Okay, so I'm going to start getting things kicked off here. Before we start with today's speaker, I wanted to remind everyone that the next Vamos will be Ashwin Vishwanath from Harvard, talking about a to be determined but phenomenal topic. And so please come. And that's really the only announcement for today. We're pleased to have Sarang here to tell us, actually, I don't have his title handy, about surprises in high temperature transport. So prepare to be surprised. Sarang is faculty at Penn State. He has done foundational work in non-equilibrium and quantum many-body systems, as well as many different types of disordered systems, from quasi-periodic disorder to multi-mode cavities and lots of weird stuff. So looking forward to the surprises. Sarang, whenever you're ready. And if you have questions, please enter them in the Q&A window, and we'll pass them on to Sarang. He has a few spots in the talk where he will stop, but feel free to type the questions in at any point. So go ahead, Sarang.
All right, thank you very much, Caden. It's an honor to be part of this series. So what I would like to do today is sort of summarize a couple of years of progress on this apparently not very interesting question of, what's the conductivity at high temperatures of some very simple one-dimensional quantum models. So this sounds like something that people should have figured out in the 50s and 60s, but in fact, they didn't. And part of the reason why is it's sort of a really poor match for the conventional framework we have for studying many body systems in condensed matter theory. So the basic thing we do in condensed matter theory is we say, okay, we're looking at excitations above some quite complicated ground state, and these excitations could be very strange. They could be fractionalized. They might have nothing at all to do with the elementary microscopic particles, but the key thing is we want them to be dilute. So once we figured out what the excitations are, then we're basically done in terms of computing transport. You don't need to worry about them interacting with each other. On the other hand, in a standard cold atom experiment, you sort of don't want to be anywhere near this regime. First of all, it's very hard to get systems cold enough. Secondly, in order to maximize signal to noise, you're really best off doing something violent to the system and then watching it ring down. So the experiments naturally live in this regime where our conventional field theory approach doesn't work great, and numerical methods like TBD also don't work great because these states get very highly entangled very fast. And so this sounds bad. It sounds like you're sort of stuck not knowing what to do, but you could say, well, okay, does it really matter? Because another system where we also don't know what to do at a microscopic level is, water in a pipe, right? I certainly couldn't do a calculation that tells you that water boils at 100 degrees Celsius. On the other hand, we do know how to deal with the system. We deal with it using hydrodynamics. And the principles of hydrodynamics don't require any microscopic knowledge. All they require you to know about a system is what its symmetries and conservation laws are. And as long as there are not too many conservation laws, there's a fairly straightforward crank you can turn to figure out how to evolve the system. And the key assumption underlying hydrodynamics is that locally a system approaches thermal equilibrium. And so whatever complexity there was in the initial state sort of rapidly goes away. And all you need to worry about is sort of a small number of variables specifying the macro state of the system. Okay, so hydrodynamics of actual fluids is, of course, a deep mathematical question, but for the purposes of what I'm going to talk about today, I'm talking about systems that live on a lattice, and on a lattice, momentum is not a conserved quantity, and therefore hydrodynamics becomes massively simpler. In fact, the only hydrodynamic thing that's allowed to happen on a lattice is any conserved quantity that exists undergoes diffusion. Okay, so is that actually what we see in these experiments? Well, no, it isn't, because in a variety of systems over the past 15 years, we've seen that this basic assumption the system is going to locally approach equilibrium, the sort of starting point of hydrodynamics already falls apart. And the basic reason why it falls apart in all of these systems is that they have long-lived coherent degrees of freedom. And these coherent degrees of freedom are present at finite and not very low density. And so this breaks hydrodynamics because there's too many conservation laws, and it also breaks the traditional field theoretic approaches because these objects are present at finite density, and so you can't treat them as just propagating freely most of the time, and every now and then maybe colliding. So you have to construct some new way of thinking about this regime, and that's what the point of this talk is going to be. And so because the basic phenomenon here is the presence of coherent objects at finite density, the thing that really matters of the two differences between a condensed matter experiment and this context. So two differences. The first is that things are at high energy, and the second is they're out of equilibrium. And so from what I said, it's clear that the thing that really matters is that you be at high energy and not that you be far from equilibrium. So you might expect that even if you were to go closer to equilibrium and study something like linear response transport property, which is much easier to think about theoretically, you'd see something surprising. And so in fact, if you go take the simplest model you can study on a computer, stick in a computer and see what happens, you see a bit of diffusion, but you really see this zoo of different transport behaviors. And you didn't even set out to have an interesting model here. It was just like the simplest model you could write down, and its transport properties were already extremely rich. A few years ago, I'd have given this talk going sideways across the phase diagram, and that's the story of many body localization. But today I'm going to confine my attention to the immediate vicinity of the y-axis. And the thing about the y-axis makes it special is the model is integrable, and we'll talk about what that means as we go on. Okay, so I'm going to just very quickly give you an overview of where we hope to go in this talk. So I want to first present this idea of interacting integrable systems as dense gases of quasiparticles. And then I want to use this thing to talk about linear response, where we have a pretty good handle on what's going on now. And then finally, I want to talk about some newer and less well understood stuff that's got to do with what happens if you go away from linear response. So this is my first stopping point. Is there anything yet? All right.
So I think that there are, I don't see any questions, Shimon, interrupt, but I kind of have a question about this idea that everything's diffusive. I mean, so it does at once sound really boring, and yet still somehow solids have fairly rich hydrodynamics, do they not? Is that just because there are so many different types of conserved quantities we could look at, or?
What do you mean by solids have interesting hydrodynamics?
Well, I just, I can have a metal and a superconductor. I can have spin transport. I have all these.
Oh yeah.
Really
Sorry,
just
no.
that there's so many...
I should clarify what we mean. So when I'm talking about diffusion being universal, I'm talking about the case where I haven't spontaneously broken a symmetry. So there's sort of a normal state of metals in which diffusion is universal. But of course, yeah, you're right. So superconductor is an example where diffusion is not the story. The reason for that is that if you spontaneously break a continuous symmetry, the Goldstone modes associated with that continuous symmetry are a new kind of slow mode. And so the hydrodynamics of the diffusive modes and the Goldstone mode gives you two fluid hydrodynamics. So that indeed, thanks for that question. In one dimension, this doesn't matter because you can't break a symmetry in one dimension. Okay. So let me keep going. Okay, integrability sounds daunting, but it's really quite simple. It's got to do with the kinematics of trolleys in a frictionless track. So in this case, you see that you have two unknowns, the two final velocities, and you also have two constraints on the unknowns, which are conservation of momentum and energy. And so these completely determine the final answer in terms of what you already know. And it turns out that that the only thing that's legal is that the trolleys can just exchange their velocities. So if this guy comes in with V1, this comes in with V2, then this guy bounces back out with the other velocity with V2, and that goes out with V1. So the velocities permute amongst the quasiparticles, but they don't randomize. A particular distribution of velocity stays the same at all times under two-body collisions. Three body collisions, of course, break this because there you have three unknowns, but still just the same two conservation laws. Two-dimensional scattering is also not like this because there you have four unknowns and three constraints. And so, you know, this guy doesn't look particularly like he thinks the outcome of a scattering event is predetermined, right? So anyway, so you do randomize the velocity distribution, and you don't really have that many non-trivial integrable models here. But in one dimension, three-body collisions often do obey a factorization condition that means you can sort of fold them into sequences of two-body collisions. In that case, the model is integrable. Okay, so integrable systems are famously exactly solvable, and that notion of exact solvability comes with a bit of an asterisk. So what people mean by saying that is that you can construct these objects called quasiparticles or beta quasiparticles or rapidities, and you can compute the energy of any state in terms of the energy of the quasiparticles it contains. You can think about the quasiparticles as like a labeling scheme for eigenstates and figure out what the energy of the eigenstate is in terms of its labels. And so that allows you to do thermodynamics because all you care about there are the eigenvalues, but the actual eigenstates are a mess. And anything involving eigenstates, like the matrix elements, the physical operator, you might as well not have a solution. You can, you know, the solution exists, but it exists a determinant that you can only compute on systems of size like up to 20 or 25 in practice. So it's exact solvability is not buying you a lot. And so, in fact, most of the progress in this field has come from this recent idea that sort of does away with the exact solution and goes back to constructing an appropriate trolley-like picture. So let me say that again, but in meme format. And so that's I think so now we're going to go talk about trolleys again. Okay, so if you want to study the motion of you know, a bunch of trolleys on a track, you realize immediately you don't want to think about an individual trolley because it keeps changing its velocity and it looks like it's moving randomly. Right, that's not the correct basis to think about this in. The correct basis is to follow a velocity as it moves from one trolley to the next. Because in that case, you know, life is simple. This object, which I'm going to call a quasiparticle, just keeps moving with the same velocity, and every now and then it undergoes a collision and it picks up a collisional shift. And so this combination of ballistic motion and jitter is the basis of this idea of generalized hydrodynamics, the quasiparticle picture. So it's been known for a long time that if you want to study the sort of long distance asymptotic regime, you can think about quasiparticle motion semi-classically. So Sachev figured that out in the 1990s. But the thing they didn't know back then, and that got figured out around 2015, is how to correctly figure out the density and other properties of these trolleys in a general state of a system, and so this is actually it's fairly simple to you know the thermodynamics of the model because that's the part that's easy to solve using beta ansatz, and so you can figure out how much the quasiparticle being there or not changes the charge of the system, and so that allows you to associate a charge to the quasiparticle, and similarly you can sort of associate address velocity of the quasiparticle by sort of integrating the effects of all these scattering shifts in some mean field like way. And in fact, this sounds kind of heuristic, but it was proved recently that at least at this level, GHD is actually exact. Okay, so the thing that comes out of this quasiparticle picture kind of immediately, though, is that whatever naturally pops out is going to be ballistic. And so you might expect the transport in integrable systems is always going to be ballistic, but it's going to be a ballistically moving quasiparticle that carries whatever charge you want to see transported. And so now you have a problem because I just showed you previously the XXZ model is not ballistic everywhere. It has this very large regime where its transport for spin is either diffusive or super diffusive, though energy transport is always going to be ballistic. And this transition lines up suspiciously with a quantum phase transition at zero temperature in the same model where the model goes from gapless to gapped. Of course, you're at high temperature, you don't care about a gap in principle because you're way above the gap. So, why does this even matter? So yeah, the two questions you'd ask you. The first is, it looks like there's a phase transition happening in a one-dimensional system at finite temperature. That sounds crazy, right? Because you're not supposed to have phase transitions in one dimension at finite temperature. But okay, we're all used to the existence now of many-body localization, and so this is another member of that family of transitions that happen in one-dimensional systems at finite temperature. The more surprising thing in some way is it's an integrable system. Why isn't it transporting stuff ballistically? Why is it transporting some stuff ballistically and other stuff not ballistically? So that's what we're going to address. I'm going to talk mostly about stuff that happens in the Heisenberg point and on the easy access side. So the basic answer I want to just outline before I go into details is that in an integrable system, the elementary excitations above the ground state are always good excitations of the system. They remain stable even at high temperatures because they've got nothing to decay into, right? So you start heating up the system, you fill in elementary excitations, you put more of them on top of the ones that exist, but the ones that exist can't decay into anything. So these guys, these Goldstone modes and domains and other constructs you made up at zero temperature persist in some highly normalized way, which you're going to figure out at any temperature. And so the reason you can have a phase transition at high temperature in this model is that the quasiparticle character changes. The character of elementary excitations changes, of course, because of ground state phase transition. And because the model is integrable, that change in the character of excitations sort of just turns into some other abrupt change in transport properties at high temperature. So that's where we're going. Okay, so let me stop once again if there are any questions. Nothing? All right.
Well, so again, I have a question. I'm deferring to Shimon for any of the other questions, but so you're referring to this as a phase transition, but this is a phase transition, I guess, like you said, very similar to how NBL is, right? There's no thermodynamic signature of a transition here. It's purely in transport, or?
It's purely in transport. And that's right. It's the same thing as NBL, right? Where the conductivity once again has a change. The conductivity is not a thermodynamic property, and so it's allowed to have these transitions even when the thermodynamics doesn't.
Okay. And would I see this in other sort of dynamic variables? Like if I looked at a spectral function or something, would that also show signatures?
Yes, we'll talk about that a bit. We can say a few things about that, but I mean, the conductivity, if you like, is the second moment, the spectral function, and so that's something that's easier to compute directly in the full spectral function. So we know less about the structure factor than we do about the conductivity.
Thanks.
All right. Anyway, so let me start out with an explanation of what's happening if I'm at very large easy access anisotropy. So that's the limit where delta in this model is much bigger than 1. So to leading order, I can think about my model as just consisting of the ZZ term. And so what the ZZ term does is it makes domain walls costly. Right, so domain walls cost an amount of energy delta, but I mean, and you can and the eigenstates are bit strings, and you can assign energy to every bit string. Okay, and so we're going to start thinking about perturbing around that point, and so the XX and YY interactions are like a flip flop, and so they allow you to move spins around. And so spins are allowed to move freely in perturbation theory if they don't change the number of domain walls. But if they do, for instance, if I have an up, down, up, and then I try to move the two ups next to each other, then that's changing the number of domain walls by 2. And so that's far off resonance in perturbation theory. And so this ends up being quite constraining because okay, let's think about the ferromagnetic version of this model, and let's think about what happens at low but non-zero temperature. So there you have a bunch of domains of all sizes, and so if you were talking about the Ising model, a domain could either grow or shrink by the motion of the domain walls. But here, the total number of upspins is conserved, so you can't move a domain wall like that. All you can do is you can sort of move the entire domain over by some number of sites. And that, for a big domain, for a domain of n spins, that's an nth order process in perturbation theory with a massive denominator. So effectively most domains that are big are immobile. The only things that are really mobile are these one spin, are these single up spins in a sea of down spins. We're going to call them magnons. And so the key thing that happens in this model is that the magnons move ballistically, but when a magnon meets a domain wall, it goes through the domain wall by this process where it flips its polarization. So the magnon started out up here as a black spin in a white background, but in order to propagate into this black domain, it had to convert into a white spin on top of a black background. And so, on average, in a thermal state, it's going to be black and white half the time, and so it has no net magnetization, and that's why there's no ballistic spin transport in this model. And this also suggests to you what kind of spin transport there actually is, because by the following very simple argument. So you let the magnon go for a time t. It's seen a region of system of size t, and that region is even if the global system were zero magnetization, you'd expect there to be just thermal fluctuations of size 1 over the square root of the size of the region from central limiting behavior. And so the magnetization seen by this guy is only 0 up to an uncertainty that's 1 over the square root of time. Yeah. And so if you say, okay, as my magnon goes through more and more of the system, it gets more and more depolarized, but it's never perfectly depolarized. You can see that the amount of magnetization transported is it's the distance traveled times which is VT over the magnetization on that scale, which is 1 over square root of time. And so what you find is that x squared, I mean, the distance, the amount of magnetization transported scales, it scales diffusively. So x squared goes as t. So x goes as square root of t. So this is not normal diffusion where you have a particle that's undergoing a random walk. Where it really is, it's an object that's moving ballistically and transporting energy ballistically, but it's getting increasingly screened as it goes through more and more of the system. So that's the origin of diffusion. And so by turning the crank a little in ways that are kind of boring and I won't go into, you can extend this idea throughout the easy axis phase. And basically what you have to do is you have to say, not only can single spins move at some velocity of order 1, but pairs of 2 guys can move at second order in perturbation theory, and clumps of 3 can move at third order in perturbation theory, and so on. You have a sum that you can do over these species, and this is what the sum looks like. And so it gives you a curve. I want to point out 2 things about the curve. The first is that if you go to the very large delta limit, the diffusion constant doesn't go to 0, it goes to some universal number you can compute. That's given purely by the magnons moving in this frozen sea of domains. The second thing I want to say is that as you go towards the Heisenberg point, as you might expect, you're hitting a phase transition. This diffusion constant diverges a characteristic critical exponent that's 1/2. Okay. So that's what happens at half filling. There are a couple of immediate predictions you can make for what happens away from half filling in this model. So the first is that the up and down domains don't cancel out exactly. There's some residual excess of the ups over the downs, let's say. And so that means that this the magnon doesn't depolarize completely. It carries some small amount of ballistic transport, which is sort of, it goes to zero smoothly. The weight in these wings goes to zero smoothly as you hit as you hit half filling, but the wings never actually close. They just sort of become increasingly faint, and eventually you can't see them. And in addition to these ballistic wings, you have this big blobby background that's left over near where the particles, near where you started out measuring, and in fact, this blob is not diffusive. It's like slightly super diffusive, and it becomes exactly diffusive exactly at half filling. So this looks ballistic, but if you look at, say, an autocorrelation function locally, it's not going to go as 1 over t. It's going to go as 1 over t to some anomalous power that varies continuously throughout the phase. And so there's a sort of phase diagram versus magnetization and then isotropy that demarcates where this anomalous local autocorrelation function exists. Okay. So that was all in the exactly integrable limit. And so now we're going to talk about what happens if, like a realistic experiment, you're not precisely integrable. And so this raises always a methodological problem. What you really like to do is you'd really like to solve some non-integrable problem. But I mean, non-integrable problems aren't solvable. You don't have any way of saying anything exact about them. And it turns out, for reasons that a bit complicated, that even numerical methods like TBD work worse for non-integrable systems than integrable systems. So how do you make progress? The one thing we found that actually worked really well was you add some integrability breaking perturbation with a space-time random coefficient. And so, you know, an individual realization of this is computationally very expensive. But if you care about noise average dynamics, you can rewrite this as a Lindblad-Master equation. And Lindblad-Master equations don't have the entanglement growth problems that that unitary evolution does. And so you can actually go to quite long times and get nice data if you break integrability this way. And it's, you know, for our purposes, we really care about some basic question about what happens when you break integrability. So it's okay if we break it any way that you know, gives us something to compare against. Okay, so that's what we're going to do, and what do we expect to see? So if this were a conventional integrable system with ballistic transport, then what would happen is the quasiparticles would pick up a mean-free path, and the mean-free path would be associated with a diffusion constant that blows up in the integrable limit. Right, but this is different because we're already diffusive in the integrable limit. And so, you know, you could ask, well, what happens to systems already diffusive? The first guess you might have is that nothing really happens. It was already diffusive. You're going to like get some correction to diffusion constant, but nothing drastic. Another guess you might make, which is inspired by this quasi-particle picture I explained, but sounds crazy, is that, look, you know, we got diffusive transport by taking ballistic things up here, and including the depolarization of the magnon as it goes through the background. Now, if you just take that argument and make the quasi-particles diffusive, you replace all the t-squareds with t's, the t's with square root of t's, and you immediately find out that you actually get subdiffusion. So diffusion goes to subdiffusion with this exponent, x goes to the 1/4. And it sounds kind of weird, and I certainly, you know, abandoned this back when we first thought of it. But then Jacopo Donadis did some numerics, and it turns out that what's actually happening, sort of, it's even weirder at some level. So you have a big subdiffusive window. So let me explain what this graph is showing. So don't worry about the many curves, just look at one of them. D of t is basically it's x squared over t. And so, you know, x squared is d times is diffusion constant times time. So if you take x squared and divide it by t, you get some effective time-dependent diffusion constant, right? Which and so if you're subdiffusive, this time-dependent diffusion constant should go to 0 as time goes on. In fact, what you find is that it goes to that it decreases over this parametrically large window, and it eventually saturates to some value, some value of the diffusion constant. And this value of the diffusion constant that it saturates to is independent of the strength of the integrability breaking perturbation. So it's like weak noise and strong noise give you the same, or not so weak noise give you exactly the same diffusion constant up to minor corrections, and it's sort of off. It jumps from its value at the integrable point. Okay, and so I don't want to bore you with details of how you argue this, but let me just explain very quickly what's happening. So the first thing that happens is that the magnons are in fact scattered by the noise, but the other thing that happens is the number of magnons is not precisely conserved, because what happens is that at some rate, a big string can break up. It can sort of hop virtually over one site, creating two new domain walls that pays an energy cost 2 delta, but then the noise can then put it on shell, and so now you've broken a string into 2 magnons, or you can recombine 2 magnons into a string by the same process. And this 1 over delta squared, 1 over detuning squared should be familiar to AMO physicists, because it's the same thing. It's the same factor of detuning in spontaneous emission. And so anyway, a fairly straightforward continuity argument tells you that you have to end up this way. The origin of it physically is that the thing that's killing diffusion is the backscattering of magnons, and the thing that's sort of restoring diffusion is the creation and destruction of magnons. And both of these scale the same way with the noise, and so that scaling cancels out. So crossover times for going from one regime to the next obviously depend very strongly on what the noise strength is, but the asymptotic diffusion constant doesn't. In fact, it only depends on the extent of anisotropy. When the anisotropy is infinite, subdiffusion persists forever in this model. Okay, so this is just showing that the noise wasn't really special. It just let us go to late times, but you can put in Hamiltonian perturbations as well, and you can see this downturn in the time-dependent diffusion constant. So these guys also have a subdiffusive regime, but numerically we can't resolve the endpoint of the subdiffusive regime. Theoretically, we believe it should go as 1 over delta to the 3 halves. Okay, so that's a summary of this part of my talk. Yeah, so we get diffusion from the screening of magnons due to thermal fluctuations, because the magnons are ballistic. When the magnons themselves are diffusive, the same mechanism gives you subdiffusion. Even when you do have diffusion, the diffusion is sensitive, very sensitive to filling. The moment you go away from half filling, you have this sort of weird behavior where the ballistic wings and an anomalous blob at the origin. So this, I guess, is another good point to take questions if there are any.
Great. So there was a question saying that it's not obvious that eliminating entanglement propagation is enough to make computation easy for a non-integral problem. So I thought 3 or more body problems can still be hard classically. Is hard just a statement that they can't be calculated exactly but well approximated, or does it have something to do with being in 1D?
Yeah, no, I mean, by easy or hard, I'm really just thinking about the complexity of TEBD simulations, and the complexity of TEBD simulations is precisely controlled by the entanglement of the state you're trying to describe. So state never gets very entangled, your TEBD runs fine, and you can take it out to late times.
Even for a classical 3-body problem?
Well, I mean, you can't solve a classical 3-body problem using TEBD, but yeah, I mean, you can simulate it in a computer just fine.
Okay, and can you comment on connections to experiment? Are there currently experiments that can reproduce or confirm your prediction?
Wait for the last part of the talk.
And another question was, do the boundary conditions matter at all? So if you compare, if I'm in a finite size system, or I have periodic or anti-periodic.
Yeah, so that's important, right? Because yeah, I should say this. So in interacting integrable systems, you really want to be on a ring. You want to have periodic boundary conditions because you want to have plane wave eigenstates you can build your beta states out of. If you have open boundary conditions, you're going to be integrable until you hit the edge, but then like weird stuff can happen once you hit the edge in general.
Great. That looks like that's it for now.
Okay, great. So let me keep going. How much time do I have?
I think we will go until 3, but it's nice to, leave some time at the end for questions. But...
Fine. So I guess it's currently like 2:40. Okay, fine. So I don't have that much left to say. Anyway, so that was the relatively simple case that was the easy access regime. And so now I want to do the slightly more complicated case that's the Heisenberg model. By the way, it shouldn't be too surprising that the Heisenberg model is experimentally realizable. That's why people have been studying it for ages. Right, so when you go from the easy access regime to Heisenberg point, the nature of your excitations changes because now you don't have domains. Now you have a system with a continuous, with a continuously broken symmetry, and associated with that continuously broken symmetry are Goldstone modes. So I mean, okay, so sorry. It's a continuous symmetry. It's a continuous non-abelian symmetry. It's not broken. But if it were broken, let's say by the ground state, which is the case we're typically going to consider, you would have Goldstone excitations above that broken symmetry state. And in this case, so this is like the one bit of beta ansatz I need to use in this talk. No matter whether your original state, whether your original Hamiltonian had ferromagnetic or antiferromagnetic couplings, when you're constructing beta ansatz states, you always begin with a ferromagnet. And you sort of start the ferromagnetic vacuum, and then you sort of pile quasiparticles, you pile spins on top of it. And so in the beta ansatz, you do this, there's a sort of fake symmetry breaking that you have to do because you have to pick a ferromagnetic direction to start piling on quasiparticles from. And so that sort of beta pseudo vacuum, in some sense, has the fluctuations that beta pseudo vacuum can be thought about. If you have, for example, if you have a region, if you have a bunch of downs, and then you have like a big sort of windy spiral that goes from down to up and then back to down, you can think about that either as a giant Goldstone-like excitation on top of the ferromagnetic ground state, or you can think about it as local rotation of the orientation of the ground state. Those are both sort of sensible ways of thinking about the problem, and which one you choose depends on how you want to solve the problem. But anyway, the key thing for our purposes is that you have these Goldstone excitations when you start filling up the spectrum above the ground state. And in this model, because the Heisenberg ferromagnet non-abelian symmetry, it turns out that these excitations have a quadratic dispersion. So frequency goes as k squared. This is different from normal linearly dispersing Goldstone modes, but it's a very general property of ferromagnets that break a non-abelian Lie group symmetry. Okay, so the velocity of the mode at momentum k goes as k, and so in general that'd be the entire story. You have linearized dispersion, Goldstone modes. You create a packet it disperses. But what happens because the model is integrable is there are actually stable packets of Goldstone modes that you can think about as solitons, and you can actually construct them as solitons above the ground state. And these solitons have properties you can sort of identify just by thinking about the Goldstone spectrum. So the soliton of size s has momentum. It involves momenta up to 1 over s, and so its velocity goes as 1 over its size. The energy also goes as 1 over its size for similar reasons, because that's the total amount of twisting you have to do to create a packet that's that size. And similarly, the soliton changes the magnetization where it is, and so if its size is s, the magnetization associated also scales as its size. And finally, if you're sitting in a state at a finite magnetic field, then Goldstones or rotations of the vacuum that are much that are much smaller than a particular critical size don't realize there is a field, so they're unaffected, but very big, very large Goldstone solitons are going to be suppressed because they cast too much energy in the presence of a magnetic field. Okay, and so at any finite magnetization, this distribution of objects of all sizes gets cut off by the field. But if you're at half filling and you don't have a field, then there's a scale-free hierarchy of these Goldstone packets that exist in the thermal state. There's no characteristic scale to them. That's partly because there's no characteristic scale left in the problem, right? The only scale is J. That's order 1. Okay. So one final very important thing: if a small Goldstone encounters a big Goldstone, it gets eaten up. Just like when a small domain went into a big domain in the gapped phase, it got eaten up. It lost its magnetization. Similarly, a small Goldstone entering a big Goldstone gets demagnetized. And so, in some sense, a Goldstone carries magnetization until it encounters a bigger Goldstone, then it dies. So the reason this problem is more complicated than the easy access case was that there pretty much all the domains except the smallest one were just sitting still. Now here they're all moving and they're all sort of guys at every size that are running into even bigger guys and getting demagnetized. And so you have to solve that problem self-consistently, and that's slightly more complicated, but it's not that much worse. So let me quickly explain where superdiffusion comes from in this picture. The argument is quite simple. It just has 2 steps. The first is to notice that the transport velocity, the velocity at which stuff is moving, is proportional to local magnetization. Why is that? Well, it's because in a region, in any region, the magnetization is carried by the biggest soliton that lives in that region. Why is that? Because all the smaller ones carry magnetization until they hit this guy and then they die. But this guy is the biggest and therefore it doesn't get screened. So it carries all the magnetization. But okay, so if your background magnetization is H, then as I said in the previous slide, the biggest soliton you can construct has size 1 over H, but speed is inverse size, so its speed is H. So this is the important part of step 1. So the transport velocity depends on local magnetization density. But okay, now that you've gone this far, the next bit is simple. So if you look at a region of size X, once again, our old friend, the central limiting fluctuations, tells you the magnetization in that region is 1 over the square root of its size. Yeah, and so by step 1, the speed is the magnetization, which is that. So how long does it take to traverse a region of size X? It's just the distance over the speed. Distance is X. Speed is 1 over root X. And there you go. Your time scale is X to 3/2, and this is precisely the superdiffusion exponent that people had first seen about like 10 years ago, but we only figured out a couple of years ago. Okay, and so I want to emphasize that I was presenting a fairly heuristic version of this theory, but if you do this calculation with all the numbers in place, you find that you can predict the coefficient of the superdiffusion pretty much exactly in line with numerics. And the other thing I want to say is that I presented this for the Heisenberg model, but in fact, it seems that any non-abelian symmetry gives you the same exponent. And that's because they all have the same, at some important level, all of these properties are that went into my calculation are very strongly constrained by the fact that there was non-abelian symmetry that got broken, and the Goldstone modes associated with that are quadratically dispersing, and that's universal. So is this superdiffusion. Okay, so that's actually a good place for my last intermediate stopping point, if there are any questions, because after this I'm just going to talk about stuff that I don't really understand.
So I've always been surprised that you have kind of, it's either a billion or it's non-abelian. I mean, like, out of all of these, infinities upon infinities of groups, somehow all that matters is if there's anything there that doesn't commute. Can you give any insight into that?
It's really got to do with the geometry of non-trivial Lie groups. And so any non-trivial Lie group happens to be non-abelian. And so that's how it comes in. Like abelian groups tend to not have interesting enough geometry. So basically what happens is that you look, so SU2 is a sphere, and you have these two directions around any point in the sphere, and those two directions act as conjugate variables, like they're the sigma x and the sigma y. So they have a non-trivial commutator. So they're not independent Goldstone modes. They combine into one Goldstone mode. So if you have something like, I don't know, SU4, then it's a more complicated spherical thing, but all of its generators sort of break up into pairs, and those pairs form a sigma x and a sigma y. And so that's what happens. And so it doesn't happen in abelian groups, because abelian groups don't have the sort of intertwining that gives you the quadratic Magnon dispersion in the first place.
And does this have to be kind of the point group symmetry? I mean, what about like space groups? I don't even know if this
no,
makes
sorry,
sense
there's
in
an
1D.
internal symmetry. It's not a
It's
point group
always
or a
internal.
space symmetry.
I mean, are there interesting questions around this for space symmetries?
That's a great question. I have absolutely no idea. We don't. I mean, it's one dimension, right? So so these symmetries are not very very rich. Okay, is that
so? I think you
okay? Nothing in questions. All right, so let me keep going. Okay, so that's all stuff that at this point we more or less have nailed down. But now I'm going to talk about the things that we don't really understand, that I find kind of surprising. Okay, the first thing that is the nature of the structure factor at the Heisenberg point in the unmagnetized case. So Prozin computed this a couple of years ago, and I guess it was really Lubotina who computed it. But what they found was that all of their calculations were well fit by the KPZ scaling function. And so KPZ, for those of you who don't know, is this interesting classical non-trivial universality class, which also has dynamical exponent 3/2, which is why it kind of makes sense that it shows up here. But the things that it describes are things like the growth of random surfaces, random growth of surfaces when you deposit stuff on them. And so they don't sound at all like the Heisenberg model. Like there's no, in KPZ, there's no non-abelian symmetry, there's no integrability, there's none of the structure, there's noise. And we have none of that here, but we still seem to somehow flow to that fixed point. And so, why that is remains to me substantially still a mystery. There's some very interesting suggestions as to how to resolve that mystery in this paper of Leopold and Danish from a couple of years ago, but like to my mind, there's still a few like gaps in the logic that that I am not entirely sure how to fill in myself. Okay, so that's one thing that we don't really understand. But one thing you could do is, of course, you'd set out to probe it experimentally, right? Now, if you look at the y-axis in these figures, you'll sort of understand why you wouldn't want to probe this object experimentally. Like you don't, everything's happening here is inside your noise floor in a realistic experiment with cold atoms. So you might want to say, okay, what kind of other diagnostic of KPZ can we look for beyond the fact that the transport exponent is right? And so that's sort of the content of this experimental paper by Emanuel Bloch and Johannes Steyer and co-workers, including myself, I guess. I didn't do the experiments, obviously. I mean, I could if they let me, but they won't. I don't, so in an experiment, you don't want to look at the far tails of structure factor, but you do have certain other things you can do in experiments you can't really do that you can do in condensed matter experiments, for sure. One of them is you can think about single shot images of the system in the quantum gas microscope. And so that's what was done in this paper. So you create an initial state with a slight magnetization imbalance, slightly more up spins to the left, slightly more down spins to the right. and then you let it go. And then you see how much magnetization has crossed across this domain wall as a function of time. And so what you find is that, as you might expect, the mean, the thing is, instead of just looking at the average, you can look at the full distribution function of the magnetization that's crossed at time t. And so, as you might expect, the mean and the variance do exactly what you think they should do, because the transport exponent is 2/3. So that part works out. The much more non-trivial check of KPZ is what happens to the higher moments, and in particular, the next higher moments of skewness. So in KPZ, there's a prediction for what the skewness should do at late times of this distribution of transferred polarization. And we find surprisingly good agreement with the KPZ prediction in the skewness distribution. So that's suggestive. At least it was suggestive to me. And I was like, okay, this is a cool like KPZ like system. This is more evidence for KPZ. But okay, so then we and Prosen's group went ahead and looked at this full counting statistics of the amount of charge that goes across the domain wall as a function of time, and we find that it's non-trivial not only at the isotropic point, but it's even more non-trivial looking inside the easy axis phase. And there's no KPZ prediction. There's no real understanding of why this distribution is so extremely skewed in a diffusive system. You might have thought a diffusive system is just a random walk, so it should be symmetric, and that's true for a non-integrable diffusive system. But here you do seem to have these like very strange statistics of polarization transfer. So that would be an interesting thing to understand. But right now we only have some suggestive numerical evidence on it. And then the last thing I wanted to briefly flag is this question of like, I made the linear response assumption at the beginning, but suppose you break it and suppose you start talking about big domain walls, what happens to superdiffusion? That's what you'd like to an experiment, because as I said, you have better signal to noise if the domain wall is big. Right, so what GHD predicts, I believe, is that you have a crossover regular diffusion on a timescale that's related to the size of the domain wall, the size of the imbalance that's initially there, and only becomes, it only goes away in the linear response limit. Why is that? Roughly speaking, because where superdiffusion comes from is the presence of these very large Goldstone-like quasiparticles, and in an initial state that looks like this, there aren't quasiparticles that are much bigger than allowed by the magnetization on the left half or the right half, whichever half they started out at. So the distribution gets cut off, and that restores diffusion. There's another question of what happens if you cut off the linear response behavior by applying a finite electric field. And so once again, as in many of these systems of anomalous transport, what you find is that the limits of taking the DC limit and the zero field, that's linear response limit, don't commute. And if you try to take the DC limit at a finite field, eventually you're going to get cut off by the field, and your response is going to go with some non-trivial power of the electric field you're applying. By electric field, I really mean whatever acts on the magnetization like an electric field would act on a charge. And so that's something that we're still exploring, and we still don't really have a theory of it, but we have the beginnings of a theory of it, I hope. Okay, so that's about all I wanted to say today. So let me stop here, and leave this summary slide up while I take questions, if there are any questions. Thanks.
Thank you, Sarang, for the beautiful talk. So accept my applause on behalf of everyone. So let me pull up the question. So you talked about the temperature dependence, or you didn't talk about the temperature dependence very much, at least maybe I missed it, but so does temperature play any role? Do things change in the limit as t goes to 0?
Yeah, so in any finite temperature, if you go to late enough times, it looks like infinite temperature because in one dimension, the thermodynamics at any finite temperature is the same as at infinite temperature. But there's a crossover time scale that grows as you go to low temperature. So for instance, at the Heisenberg point at low temperature, you have a short time regime where the system doesn't know it's at finite temperature. And so it has ballistic spin transport. And the ballistic spin transport crosses over to KPZ behavior on at some crossover timescale at which the system realizes it's thermal.
Can you think of that as seeding, like some size of these domains or something there, thermally, or?
Yeah, so remember that, I mean, so why, okay, so let me go back to the structure of the theory. So notice that these big Goldstone solitons have energy that's 1 over their size, right? And so they're present at arbitrarily low temperatures, and the very big ones are not suppressed at all. On the other hand, the very big ones are spatially quite rare. And you can think about this as sort of like saying that in a low temperature ferromagnet, my domains are very big on average. And so your magnon has to go from one domain to the next in order to realize that it's at finite temperature. And so that basically scales as how long it takes the magnon to like traverse enough of the system to realize that it's not at 0 temperature. So that's crossover there.
So another question was, how did you calculate the full counting statistics? Was this the GHD or numerical?
This is purely numerical. We don't have a GHD way of computing full counting statistics beyond the Eulerian scale, where Ben Doyon has a paper about this. But this is numeric. So okay, let me explain why the numerics is reliable. So these are both classical models that are in the same universality class as the easy access limit of xxz. And so this is a classical model. This is cellular automaton, and it turns out that they have the same transport properties as well. And so, but you can actually compute full counting statistics, very many systems, and very late times. And so, if you were limited by TEBD times, you would never see any of this crossover stuff because it all happens on timescales that are quite long.
And another is how large is these experimental systems, and can you can you really see hydrodynamic behavior on these scales?
That's a good question. I mean, there's no reason a priori that you would be able to, but you get lucky sometimes. So these systems are about 50 sites. You can make them slightly bigger, but not much bigger. And yeah, so the fact that you can see this KPZ behavior at short times is it's a brute fact about the world. We don't have a theory of it because in some sense, hydrodynamics is not a theory that tells you when hydrodynamics becomes valid, right? It makes some assumptions and it's true when the assumptions are true, but like why the assumption's true at some given time scale is not a thing that I can really give an answer to within Hydro.
Great. So I think that's it for the questions. And let me thank Sarang again. There's going to be an after talk discussion with students and postdocs, and I will put the link for that into the chat. And I also will send an announcement, I'll put up a slide here just to remind you that in 2 weeks, there will be another VAMOS seminar by Ashwin Vishwanath with a title that we don't know, but it's December 3rd, 2 weeks from today, and there's his picture. So please, bring your questions to Sarang.